Welcome back, dear friends, after another rather pregnant pause in proceedings, but I have been very busy and I must thank the many of you who had the patience and quite possibly the caffeine necessary to watch the first version of the Automaton Head assembly instructions. It was really helpful, all the comments, thanks very much. I went through all the comments and I've made all the suggested changes. However, nothing is simple at Steamhead. This is the video editing software I use from Pinnacle 14, I think it was. I've been using them in different varieties for about 25 years, I think. And we got this one because obviously you have to upgrade to get the latest sort of codecs for new audio and visual file formats and stuff. And it works pretty well, you know, it renders perfectly whenever you finish editing. Normally there'd be a huge, about 8 of these tracks with audio and visual and titles and all sorts of stuff, but I'm still working on this video and it takes ages to render all the images, so you just have to believe me. But I'd finished those instructions for the first, the assembly, and it's all well and good when you're sort of adding bits onto the right hand side, you know, you're dropping clips on, trimming them, editing them, and you can keep going into the future. But, dear friends, if you want to go back and say, I want to split this clip and I want to insert something there, when you try and do that, all of the clips separate from where they're aligned to audio tracks and video tracks and titles. It all goes out of sync. It's not meant to. Every sort of video editing software has a couple of little buttons here, so you can sort of group things together and say, shift everything to the right and let me slot something in there, don't move anything else. This says it does in the instructions, but it doesn't. And I have no idea why. I've gone through all sorts of conspiracy theories. I have a feeling, in fact, that's right, because what I was having to do was to move everything to the right with a huge gap, then do the little work fiddling around bits, and then move everything back and line it all up again. And I'd be able to do about 4 or 5 single edit jobs before it would jam up, and every single edit job would then take about 5 minutes to render, so I could then watch it and see what it looked like. Absolutely ridiculous. So then I'd have to save it, reload it, then do another 4. It took me 2 days. It's ridiculous. These are actually the instructions that I'm going to be releasing after this video that I'm currently making, because these are the instructions that are going to explain how to wire it up. But mustn't grumble, I got it done. Yeah, so actually what I was going to say was I think they actually removed those buttons when they realised that there was a problem with editing halfway through, and rather than trying to solve the problem they just took the buttons off. Anywho, mustn't grumble, as I said. So these new electronics instructions, you wouldn't credit it, but I've got resources. I've made resources. I've planned ahead, because we need to work out how to connect the Teensy up and go through all that sort of thing with people who may not be aware of how to or not really understand it. So I've made that video, and here's the circuit, and here she is, all wired up. What I'm doing now is I'm improving my Arduino or Teensy sketch to get her to move how I want her to, because in the original one I simply wanted her to look up and down, open her eyes and say some stuff, move around randomly. This is in the loop, as you can see. Look, every single thing I wanted her to do, this is just blink or something. Move sequence 1, that was 0, 1, 2. Every single thing I had to type in, and then you'd get clashes, and sometimes if her eyes were moving randomly or blinking randomly and then you did something else and it would stop working. Oh, look at this. It was should have been so simple, but look, the new one, I've written some rather clever, if you don't mind me saying so, functions that you can just list. There's the loop, and you give it a couple of information. Each function has got a number, so it knows which order to go in. You can have things like wait, and it will wait 3000 milliseconds. Eyes open, left, right, degrees, wait, which means it'll move up to 180, but it won't move on to the next step until it's done that. Oh, there's so many things. Eyes right, eyes random, that's right. And left, right random. So I've got all these functions, and it's been really difficult to write because they all use the millisecond timer, not millis, because Teensy, and apparently there's a library for the Arduino, has something called elapsed millis, that's it, which is really handy because it takes care of all the long, unsigned long numbers and the 49-day rollover when the Arduino runs out of room and goes back to zero, and it can catch you out and things. It takes care of all of that. It's lovely. It's a variable, and you can just reset it to zero, and it's always counting up. So you reset it to zero. If you want to wait a second, say, is it 1,000 yet? If it is, do something. But that means, because I want her to be able to blink randomly, move her head up, down, left, right randomly, and do all sorts of other things at the same time, that it's having to address loads of these instructions simultaneously, always looking through all these numerous timers to work out what it should be doing next. But let me show you. I think I've just managed to iron out the last lot of issues. As I say, it could be operating loads of these instructions in the background. You know, when you ask it to left, right, random, it's going to keep reading that and keep waiting and doing things, and eyes random. But this is just a simple one. It's going to wait 3 seconds, eyes open, move to the right. We're going to wait for it, which is so handy. Because in the past, whenever you moved her to the right or left or up and down, you then have to have a wait afterwards to make sure that it had time to move that far before moving on to the next instruction. But this just, it's a joy. Little things. So it goes 180 degrees, 90, 0, 90. This is just a test, a combination of things. Eyes closed, then you wait another 3 seconds, then left, right, random. She's going to start moving randomly at random points and distances, left and right, and the eyes are going to be random. And then after, wait for 30 seconds doing all that, then move back to the centre, wait 3 seconds, and then the eyes close. Shall we see? I've uploaded it, so I'll just press the reset on the Teensy. And I'm not worrying about the speaking yet. I'm going to do that afterwards. I'm just thinking about the instructions for how to wire her up so she can actually move. So she's closed her eyes, and then hopefully she's going to start twitching and moving and blinking and things in a random way. And I'm using the fantastic Teensy entropy random library because that actually adds proper randomness by timing the difference between the internal hardware clocks and the Teensy, apparently, because otherwise you just keep reading the same random numbers off the stored list inside, and she'll do exactly the same thing every time. So there we have it. That's exciting. The thing is, once I start, I just can't stop, because the next thing to do is to think about programming the speaking and things, which I said I'll get onto in the next lot of instructions. However, in the meantime, also, I have been printing quite a lot of stuff. I've been printing heads, and then I noticed with these ones, because I had to slice it into 3, and then I put them back together because it was all the files were corrupted when I was designing her. I noticed there was a sort of ever such a slight line. You can't. Oh, perhaps you can see it on the end of her nose, where I'd rejoin them, and I spent hours on Blender trying to work out and remember how to use it in the first place. Then tried to smooth these over, and I just couldn't. So I gave up. But then the next day I thought, no, this has to be possible. So I spent ages on 3D Builder, really carefully positioning, because they'd snapped into place when I put them back together, these 3 slices, and but not quite. So fractions of a millimetre, and then it now prints perfectly. I was so pleased about that. Also experimented with the head, because I had that improved hair. Rather than printing the whole lot, was giving her a lobotomy or something. So yeah, I've just printed that bit to test, and it does fit perfectly. I've received my first order, which is very exciting. So we've got all the bits necessary here, the lovely hair, and I am now printing a bald head because the customer wants one of the bald versions because he's going to provide his own wig. Oh, and I also got the website. My website's updated. I'll put a link on the screen with the information on this automaton head kit, which is really exciting. And I even managed to add a PayPal button, ordering button, on the web page. That is another story altogether. I get a dream. I have a dream, and I know what I want to achieve, and I am so tenacious. It's a curse, I tells you. But with the help of ChatGTP, in the end, having torn my hair out, what remains of it, I managed to get it to change the code provided by PayPal, which had an error in it or something or other. So it does work on the mobile version, the narrow version, and the desktop version. So that was lovely. It is worth doing this sort of thing because the joy that you feel when you don't believe it's ever going to work, and then it does. Right, I have a touch of the old verbals, as you can hear, and it's lovely to be able to speak to you again. I've just been, as I say, I've been so busy and focused on getting all this stuff done. It's taking ages, but it's enjoyable. So, thanks very much for tuning in again. You can now have a preview of the how to wire it up instructions as far as I've got. So, hope to see you next time when it'll be a more personable one. Welcome back. In this video I'm going to explain how you can get the automaton head that you're either thinking of making or have made to actually work. I'm going to explain the sorts of motors that it uses, how to connect them to a microcontroller, which microcontrollers you could use and how to connect them up, and finally how to program it so it will actually move how you want. There's a servo motor, two of them, one moving her up and down and one moving her head left and right. There's a small DC motor that we use to open and close her eyes. And there's a small 5-volt solenoid which we use to open and close her mouth with a very small spring that easily flies across the room and you can lose, so be careful when you use it. So we need a way to get the outputs from a microcontroller to be able to control the large amounts of current that the motors and the solenoid draw. So the microprocessor can send out a low current signal to the servo motor, and that signal can find its way back with the common ground or 0 volts. The motor inside that needs lots of current can get whatever it needs from the 5-volt supply. So the only current leaving the Arduino microprocessor is very, very little, probably about 1 or 2 milliamps, which is absolutely fine. So if we're desperate to see the automaton head moving, or to set up a servo motor in the right position before we assemble it, we need a way of controlling them. And there's a very handy little module that you can get from AliExpress, I think. I'll put a link in the description. Here's one I purchased earlier. Very handy. It was recommended to me by a couple of kind people. It's got 3 modes, one that sweeps the servo motor backwards and forwards, one that sets it to the middle position, which is handy, and one that you can control it by moving this. All you need is a 5 volts input. I'm just using my power supply, and one feature of this, very, very bright blue LEDs, incredibly bright. Alternatively, you could use a microcontroller such as an Arduino to control the position of the servo motor. Arduinos are great because in the Arduino IDE, if you go to examples, it comes with one called servo for the servo library, a knob. Basically, if you open that, it's a simple sketch that includes the servo library and reads an analog input from the potentiometer and then sends that out to the servo motor like so. So when I turn this, you can see, depending on the position of the potentiometer, it's controlling the servo motor. So that's nice, and this is wired up in a slightly different way because we've got 2 supply voltages. We've got 5 volts from the power supply to drive the motor with lots of current, We've also got 5 volts from the computer, the USB lead, to run the controller. So if you have a look at the circuit for this, we've got 5 volts from the power supply, 0 volts from the power supply, connected to run the servo motor, like half an amp. We've got the output from the Arduino connected to that, and we've got the Arduino being powered by the USB 5 volts, USB 0 volts. But because all the 0 volts are connected together, it'll still work perfectly. That's the thing to remember. So without more ado, let's get her head connected up and get her looking up and down and left and right. So there she is, and here are the wires that exit from her neck. Now there are 2 servo motors, as you can see. You know which one's which, because the longer one is the one that's nearer to the base, so that's the one that makes her look right and left. So let's connect that up. I've sat her on a little wooden platform just so that the wires are free to rotate underneath as she does. So when I turn it, you can see that she looks hard left, is that? Right. So that's lovely. What fun, that tells you. So the up and down servo motor is situated at the top of her head, so the wires are slightly shorter. So as you turn the servo motor right round to the one extreme limit, she's looking up, round to the other extreme limit, and she's looking down. I was very keen to design it so that you could put any angle in and it wouldn't cause any damage. Nothing would hit into anything else. Now we want them to move slowly because servo motors are designed to move very, very quickly from one position to another. We don't want that because it'll look silly and also put lots of strain on the mechanisms. So we need the servo motor to move slowly, and I'll explain how to do that when we come to programming. But it is possible. You can see I've been using Sharpies to draw with. What a mess. The second type of motor is a little DC motor, and this is used to open and close the eyes. I could have used a solenoid for that, but it would mean that it always needs to be supplied with electricity to keep the eyes open or closed, whichever way it was mechanically connected up. This is great because it just needs a really short pulse to get it to open the eyes one way, and a really short pulse in the other direction to close the eyes, and then they'll stay open or closed. So that's nice, but we need a way, therefore, because this is another motor, and therefore it's going to draw quite a lot of current, far more than a microcontroller can provide, so we need some sort of way of connecting a microcontroller to it. And what we use is called an H-bridge controller. Here's a typical, very common H-bridge controller. It's actually a dual one. It's got 2. You can connect one motor there, DC motor there, and another DC motor, or equally something else, to control there. And it's got supplies and the little control inputs and logic inside. So these control inputs take very, very low current, sort of like 1 or 2 milliamps. And this can control, I think, up to about 2 amps per motor. So that's plenty. Inside, it looks like this. It's a sort of H shape, which is why it's called an H-bridge. So we've got the typical 5 volts at the top, for this example anyway. It could be a different voltage if for a different project. 0 volts at the bottom, and then 4 electronic switches. So if you switch that one on and that one on, the motor will go one way round. If you switch that one on and that one on, the motor will go the other way round. And there's some very clever logic to stop you connecting all of them and short-circuiting the power supply. So we need 2 outputs from the microcontroller, one to tell it to turn the motor on one way to open the eyes, and the other one to tell the motor to turn the other way to close the eyes. However, just to get things moving and see what can happen, we can just use a 3-volt battery pack. There we are. It goes that way, and if I swap it round, it goes the other. So let's connect our eyes and see what happens. It's all a bit fiddly to do, but if I connect it one way, our eyes open, and then if I swap them over and connect it the other way, they close, which is great. One thing to be aware of with any sort of component like a motor that's got coils of wires and uses magnetism is it has an inductance effect, which means when you switch it off, it creates a very large spike, a voltage spike in the other direction. A very short one, but it can be hundreds or thousands of volts, which will instantly destroy any sort of semiconductors connected to it. So to stop that, you wire a diode across the other way around, across the inductor, the solenoid or the motor. Now that's quite easy to do if you've just got one coil like a solenoid. When you've got a motor and you want to with an H-bridge controller, it's a little bit more complicated, but thankfully H-bridge controllers take care of that. You can see there are the 4 diodes that side for the motor and 4 diodes the other for the other motor. So the final device to get her moving is the solenoid that controls her mouth. So here's the solenoid that we use to control the mouth. I still managed not to lose the spring. It runs on 5 volts, but it draws about 450 milliamps, which is nearly half an amp, so quite a lot of current. So we need a way for the small output of a microcontroller to control, switch in effect, 450 milliamps. So rather than using some complicated interface module, I had a load of these floating around. These are TIP 121 Darlington pair power transistors. Inside, well, there's the outside, so we've got 3 connections, as with all transistors, a base, a collector, an emitter, and there's a heatsink on the back, because they can get hot if they switch lots of current. Inside, however, they look like that. There's 2 transistors, and they're connected together so that they can switch very large amounts of current, which is perfect for our solenoid, half an amp almost. So this is how we connect one up. We've got the 0 volts across the bottom, we've got the microcontroller there, plus 5 volts at the top. The output from the microcontroller goes through a 1k resistor, so that's 1000 ohms, to limit the amount of current that it can produce, down to about 1 or 2 milliamps. That then goes into the base of the Darlington pair. The emitter is connected to ground. The collector is connected to the solenoid that goes up to plus 5 volts. So this transistor is switching ground in effect, and there's the diode wired the wrong way across the solenoid to stop the back EMF pulse. So that's what the circuit looks like, and here's what the wired up one looks like. So we've got 5 volts coming in, we've got 5 volts going to supply the Arduino and ground, 5 volts and ground coming over to this little breadboard here, which is wired up exactly like that. And we've got the solenoid there connected across the diode. Hang on a minute, let's zoom in. There's the 1k resistor, that's right. There's the diode, which is a 1N4001, which is just a bog standard diode. They seem to work perfectly. And then the grey wires go to the solenoid, which has got a little block of wood to stop it firing its spring and central coil all over the place. And because I've connected to the Arduino is being run off everything else, just as in this drawing, when I switch it on it should do something. 5 volts, switch it on, 300 milliamps, oh look, 530 milliamps, I can hear it clicking, so over half an amp then, 530 milliamps, and there we have it. I'm actually running it off the first most basic example sketch that you get with the Arduino Integrated Development Environment, IDE, I can't bear acronyms, that blinks. It just switches an output on for a second, then off for a second, and it's doing that. So that's lovely. So that's drawing over half an amp. And the Darlington pair here is doing all the switching. Now the great thing is, because when she talks, her mouth is constantly opening and closing, it's not on for long periods of time, so things shouldn't get too hot. Might be worth putting a little heatsink on there. We'll come to that later. Well, that's all well and good, I hear you cry, but you want to see her mouth move. I'll get her connected up. That's a bit disturbing, isn't it? I think that's because normally it would be pulsed. I'll explain how to do that when we come on to the programming part. But this is just being on for a whole second. It really does open her mouth up a lot. But proof of concept. For those of you who are highly observant, you may have realised that the H-bridge controller I was using was a dual one. It had 2 motor controllers, and that one was spare, so I could theoretically use that to control the solenoid. But I did try that several times and I couldn't get it working, and I think it's because transistors always have a 0.7 voltage drop across them, just because of the way they work. So using this one, basically with the Darlington pair, that's only going to have a single 0.7 voltage drop, so that means it'll be 4.3 volts. Thank you. But when using the H-bridge driver, it has to go through 2, so that's going to take off 1.4 volts. So that's going to be 3.6 volts, which just isn't enough to run the solenoid. Hence the fact I'm not using the other one of these. The other thing to notice about these small solenoids is they do get warm. Just having that switching on and off, a second on, second off, so a 50% duty cycle, after just sort of like a couple of minutes that was getting warm. And I've realised that's why they've got such heavy metal and outer piece, because it's a heat sink for it. They're small, so having half an amp going through that is going to create quite a lot of heat. So the moral of that story is don't have her sitting there with her mouth open catching flies. However, I did design her so that the solenoid just sits in the open inside her mouth. So there's going to be quite a lot of airflow through there and out the back of her head. So to recap, got high power 5 volt supply. We've got 0 volts, everything connected to 0 volts. If we're using the servo motors, we can connect them directly to outputs on the microprocessor. And there's 2 servos, up and down, left and right. For the eyes opening and closing, we've got the small DC motor, and that can be controlled by 2 outputs on the microcontroller. One to get the eyes to open, one to get the eyes to close. And again, 5 volt supply from the power supply, everything connected to 0 volts. And finally the solenoid, plus 5 volts from the power supply with enough current to supply half an amp to that solenoid, plus the other motors and things. The Darlington pair connected to ground, and again an output from the microcontroller through a 1k resistor into the base of the Darlington pair. Not forgetting the back EMF diode. Yes. So now it's time to think about microcontrollers, how to actually get these interface devices to control the different types of motor that we're going to use to make our face move. I use Arduinos to control most of my machines, but they're not fast enough to be able to play audio files from an SD card without another huge module attached. Now I appreciate there are so many different types of microcontroller and lots of people have their personal preferences, and that's absolutely fine. I'm just going to talk about the Teensy because it's the one that I've used. So I'm going to use a Teensy and a Teensy soundboard. They come separately. So there's the soundboard with a slot for a micro SD card to store audio files on that can play, and there's the Teensy that can control all the functions of the audio board, plus do all sorts of other things like control her movements while it's playing a multitude of audio files simultaneously. It's amazing. So to join the two together, you just need 2 rows of 14 header pins, just the standard ones, having taken me a long time to realise how to fix the two together. Simply ridiculous. But they stick out far enough so that you can solder them onto the back. 2 rows of those, and then you can solder the Teensy on the top, just ensuring that the pin numbers line up properly. You don't get it upside down or the wrong way around. So once you've got the Teensy connected to its sound shield, just looked it up, that's what it's called, there are a couple of things to consider. The first thing is that 10 of the general purpose input outputs are actually used by the sound shield, so you can't use them. After very little research and lots of mistakes, I can confirm these are the ones you mustn't use. These ones, however, you can, and these ones can work as pulse width modulated outputs, those two. All these are analog inputs on this side, or the normal digital input outputs, and on this side we've got the digital pulse width modulation, all the rest of it. So that's nice. So it leaves you with 10. There are a load more connections underneath here, but now you've soldered them together, you can't actually get to them. But this should be sufficient anyway. So the second thing to remember, be aware of, is that you obviously can run the Teensy from a USB supply, 5 volts. It's also got an input which can run between 3.6 to 5.5 volts, not above that. Either way, But the Teensy itself actually runs at 3.3 volts. It's got a regulator on the board, which means when you use these as inputs, they mustn't go above 3.3 volts, otherwise it will damage it. So to reiterate, you can run the Teensy from either USB 5 volts plug-in lead or from a plus 5 volts connected to the 5 volt in, but not both, not at the same time. I've checked and they clearly state you mustn't use them both at the same time. You connect the ground to the common ground or 0 volts. If you want to have a switch connected to one of the inputs, set as an input, you connect the input to the switch and then the other side of the switch to ground. So the switch is actually switching to ground, on and off, so to speak. And then you set the input to input pull-up in the sketch, we'll cover that later. And that in effect connects a resistor to the 3.3 volt supply inside the Teensy. That means that the input is always high, is always on, until you switch the switch, and then that pulls it down to ground. That way it won't damage the Teensy because it's not switching 5 volts. If you want an analog input, say with a potentiometer, again that mustn't exceed 5 volts. It's very easy to make the mistake and connect one of the legs to plus 5 volts, but that would mean that as you turned the potentiometer, or the volume control so to speak, up, that input, the analog input, would go to 5 volts, and again that would damage it. So always make sure, if you want to have potentiometers, that they all connect to the 3.3 volt output on the Teensy. So this is how I'm going to wire my head up. This is what I recommend you can do. I've got 5 outputs. I've got one to run the mouth solenoid, which is just on or off. The eyes H bridge, number 1 input, so that might make them open or close, I can't remember which one. The up-down servo, that's a pulse width modulated output, and the left-right servo, which is another pulse modulated output. And then the eyes H bridge, number 2, connected to another digital output. And then that leaves me with the other 5 general purpose input outputs to do with as I wish. Let's get it wired up. Here's the circuit diagram from before, so this is how we're going to connect it all up. I'll get that done and then we'll have a look and see what it does. So we've got the head with its wire sticking out, we've got the Teensy with the sound shield, we've got the H bridge interface that's going to control the I motor, the DC motor, we've got the Darlington pair, the diode and resistor that's going to control the mouth solenoid, and I've got some acrylic cut out with holes so I can mount all the bits in the right place, but you could use a bit of wood or anything else, just screw things down onto. All these pieces have nice big mounting holes. I'm going to use also a bit of prototype board to mount the Darlington pair on, and a little strip, cheeky little strip, I'm going to glue onto that I'm going to use to join all the grounds, the 0 volts and all the plus 5 volts together. It's just a handy way of doing it. And I've got red wire for plus 5 volts, black wire for 0 volts ground, and some pretty colours in betwixt and between, and a soldering iron and some solder. So I will get all this mounted onto that. And Ziggy thinks that it's now time for a walk, but it isn't. I've got to wait for a parcel to be delivered, so it's not yet time. Bless her. I've got them screwed down with plastic screws, nylon ones. You could use wood screws or anything else as long as they're small enough to fit through the holes. Just be aware, of course, that you have all these solder blobs underneath and bits of wire sticking out, so you need spacers. I wouldn't recommend using metal washers because sometimes the tracks are very close to the fixing holes and they could actually short circuit bits and pieces. Some sort of insulating space would be great. Now what I'm going to do first of all, and I keep meaning to say, when you're handling electronic items like this, sensitive little things, it's always a good idea regularly just to touch something that's earthed. The soldering iron is earthed, so I just regularly touch that in case I've got charged up with static clothing or whatever else. I'm going to connect all the grounds up first, 0 volts, with the black wires, and then the reds. There's actually not that many, is there? I just realised, of course, I've got one interface. Anyway, oh, and I'll build that circuit with the Darlington pair. Remember with the Teensy that you've got the USB socket at one end to connect it to the computer for programming, and you need access to that. And at the other end you've got the SD card slot, the micro SD card, so you need access to that to store audio files. And the other thing I'm going to do, just remembered, here we are, look, the end of the servo motors always end up terminating one of these three-way connectors, plugs or sockets or whatever. So I'm going to use some of these header pins and use part of this prototype board just to be able to connect them handily. Because the great thing about this prototype board is that obviously you've just got lots of thin copper strips, each insulated from the next. And if you want to break one, you just use a tool like this, which is basically a drill bit in a handle. And you can just twist it a couple of times round and it'll break one of the tracks. Here's how I've laid it out. Here's the circuit diagram. 1k resistor, 1000 ohms there, to limit the current into the base from the Teensy. We've got a 1N4004 or similar diode there to stop the back EMF from the solenoid. And the other connections, these are the ones for the two servo motors with the individual connections to the Teensy. And what's nice is that we've got ground going up feeding everything, the servo motors and the solenoid, well, the TIP121. And we've got plus 5 volts also feeding the servo motors and the solenoid. This is what it looks like once it's soldered together with the header pins connected in. So you've got a servo motor there, you've got the two outputs from the Teensy for the servo motors and a point to connect plus 5 volts and 0 volts ground. And you've got the header pins here to connect the output to work the solenoid from the Teensy, and then two connections for the solenoid. This is what the back of the board looks like, the prototype board, and I've shown with where the solder joints are, and also where I've cut holes to separate the track, to split the tracks. There's also a solder blob there to link that track to the emitter of the TIP121. And here are all the connections. Teensy connection pin 2, Teensy connection pin 4 and 5. We've got the left-right servo that can just plug straight onto those header pins. We've got the up-down servo, plug straight onto them, and the other ones can be soldered, the mouth solenoid, the ground at plus 5 volts. Nothing of joy. So different colour header pins for the different connections. Rather than having wires just going straight into the prototype board, and the problem with doing that is they're very weak, because once you've bared back the insulation, for example here, even not that much movement, and it's all focused on where the wires actually enter the circuit board, and they can snap quite easily. Whereas if you solder them onto header pins and then have a little bit of heat shrink sleeve over the top, it's really structurally sound and makes a good connection. Because the Darlington pair are actually switching half an amp, it's quite a lot, so it could get a bit warm. Always wanting to overdo everything, I've just screwed it to the base with a little heat sink to make all the difference. When you wire up this sort of H-bridge interface, there are two connections for positive volts. The one on the right is plus 12 volts because you can run 12 volt motors off using these interfaces, or any voltage below that. And there's also a plus 5 volts, which is to run the logic on the actual chip itself with ground in the middle. So what you need to do, because we want to run all of it off 5 volts, is to get rid of, there's the little voltage regulator there, the 5 volt regulator. We don't want to use that, we don't need it. So we're going to pull that little link out, and we're going to connect 5 volts to both of those inputs. There we are, the little link has been removed. So now we're providing the 5 volts for the logic and the 5 volts to switch for the motors. So now we have plus 5 volts to the interface and to my little collection of bits here, which is going to do the solenoid and the two servo motors. So that's nice, they've all got supplies. and we've got ground going to the interface for the motor, iMotor, and to my little collection of bits, and also to the Teensy. Connected that to ground. Everything is grounded out. We're not going to run this from 5 volts from there at the moment, because while we're programming it and setting it up, we want to run it off the computer. So the USB lead, when it's plugged in, will run the Teensy, and that's absolutely fine because everything's grounded, so the electricity can control everything easily, if that makes any sense. So now I'm going to wire up the interfaces to these outputs, these 5 outputs. I've got her all wired up. She's sitting on that little base so that she can turn freely without the wires rubbing against the table. I've just extended the wires a little bit longer and connected them all to the circuit. So what we should now be able to do is to switch on 5 volts and nothing much should happen. Let's try that. That's okay. No magic blue smoke released. She moved suddenly because the servo motors are both powered up, and they're not receiving any signal from the Teensy because the Teensy isn't actually on at all. Lovely. So we are all ready to start experimenting with programming the Teensy. Thanks very much for watching. I hope that was not too boring, interesting. Less boring, I suppose, hopefully, if you're actually building the circuit yourself. Next time, it's going to be working on the programming instructions, that's right, and then the sound. Oh, it's ever so exciting. Hope to see you next time. Oh, and remember to check out the web page as well, the website.